All right, there we go. So for our module 3, I'm going to start by just doing a quick review of what we've gone over so far. I realized in talking to some of you while you were doing the module 2 homework that I might have kind of skipped over something / should have reorganized how I presented this material. So we've been working a lot in these Jupyter notebooks, but the how to use a Julia file and how all of that is structured might not have gone over as well. I wish I had started just with a Julia file and said, hey, we're going to use these Jupyter notebooks because it's easier to use. So I'm just going to do a quick overview of kind of the anatomy of a Julia file. So the top of the file, and I'll open these side by side, actually. It might make this easier as we're doing this. Close this. So, and also for the rest of the semester, I'm going to work just in Visual Studio Code. No longer am I going to use Binder. If you want to continue using Binder / Jupyter Book, as it's called, feel free, but I'm going to use VS Code because I'm much more familiar with using it, and it's just got more features. But anyway, so the top of the file is always going to be including things from other Julia files or Julia modules. So things that are not defined in your file here that you are going to then reference and use. If you aren't using it, you shouldn't have the using statement. So say I put like using mathematics, or I think it's there's a math library too, but just whatever it is. Let's just say Julia Chem, a thing that I work on. We're not going to use Julia Chem anywhere here, so having this using statements is useless. So over time, you'll be changing files, and things might get moved from other things. So you want to make sure that this stuff up here is as clean as possible, so it's not having any old unused using or including. So using, pulling in packages that are external to your code base, include statements that include files from other places in the code. So we're in module 3, anatomy of Julia.jl. We can go ... which goes up a directory, and then we can go into module 2 and hello.jl. So you can move around all the file directories and get different files from different places. So everything we had seen before was just in the same folder, but you can use files from other folders, as I'm going to talk about today, kind of in software engineering and how to organize your code. We will get into that. So I just wrote some functions here that are just to have stuff in the middle of the file, defining functions, shared variables, other things that you're going to use in the code. And then you have the bottom portion of a Julia file, which I would describe as sort of the script portion. So this is stuff that is actually getting, executed. This is just defining functions, but nobody's necessarily called them yet. These statements down here are actually being executed by the computer and doing some sort of thing. So the first thing we're doing here is print hello, and hello is coming from that hello.jl file that we're referencing elsewhere. So this shortcut right here, I can control click on a function, and if Visual Studio can figure it out, it'll take you to a highlight, and you can double click it and then go out to the file itself. Just a neat little trick there. And then we're going to call the functions that we described in here. So these lines, I say they're optional because maybe we don't actually want them and we're defining some bit of functionality in this file, but it's not something that we ever call. The caller or the script could be our Jupyter file, or it could be some other script file. So just in the same way that hello doesn't have any scripting at the bottom, because it's just defining functions that can be used. And that's going to be 95% of Julia files in a code base are going to be things that don't have a script. Really, there's only going to be ever really one file. If you think about it, there's one thing that has the main function that starts the code, and then the rest of it is just functions that are getting used. So that's just kind of the basics of how a file in Julia is executed. Of course, and I kind of say this in the notes, but it's executed from top to bottom. So what you can't do is have your script stuff above where you're defining the functions, because Julia hasn't loaded those functions into the computer into memory or whatever you want to call it. It doesn't know how to do this function yet because it hasn't been defined. So that's why the scripting portion should always go at the bottom. So even if you like, let's see, do some stuff, like you wouldn't want to do this, like this, like yes, it's like related to this and it's closer to it, but that's just really confusing to like have scripting stuff then defining functions, doing more scripting stuff. It's just ugly. Don't do it. Whether I'm not even going to try running it to know whether or not if that was legal. I'm pretty sure it is, but let's just pretend that it's illegal. I've declared it illegal, therefore you're not going to do it. So there's a few things in Binder. I guess I said I wasn't going to do Binder and I don't have it open, so I'm not going to open it, but you don't have, I haven't figured out, maybe someone else has figured out a way to run just files by themselves in Jupyter. The way that you do that is just include a file, and we've done that in the Jupyter lines, where you just include the file you want to run and run it. That will load the functions. It will load the file as if, you know, as we're doing here, and then run anything. If you want more documentation on how to use VS Code and Julia specifically, you can go to that link. And then I can review some of just the basic syntax. So I'll just go back out to one of our files from Module 2, and we can see some syntax. What's a good, let's just go back to the, so println we've seen a lot of times. So we've got for loops. So you got for, declare an index in, and then you declare a range. So this code is going to get executed for each number that's in that range that's declared, and we're going to print hello world. So we compare that to sums, so we can sum, and we have another range. We have our summation plus I, which is equivalent to this plus equals. Got while loops, similar kind of thing. So we got while and then some Boolean condition. So this will either return true or false, and if it's true, it'll keep going into the loop. If it's false, it will move on to the next part of the code. I think all of this is pretty similar. Function calls, we've been doing a lot of that. So you can define a function, and you call it. So kind of the difference is you've got your function definition that has this thing. It looks very similar to this. So you call the name, you pass your variables. Arrays, I'm going to skip over this because we're doing two-dimensional arrays today, so we'll get some more practice with arrays that are slightly different. Iterating over them, length function, yeah, I think that. So I'll say this in the video for you guys, and I sent it out in an email. If you guys have questions, I'm happy to answer them. I can make specific small video clips or answer them over email if they help, so feel free to ask. I am here to help. And I will be posting the solutions to Module 2 here in a couple days. I want to give anybody a last chance if somebody's going to submit Module 2. And then if not, I'll post the solutions so you guys can see them. I think most of you that submitted it will have got it right. I haven't graded yet, but we'll grade soon. But let's dive into the topic for today. So there's two topics. First, we're going to talk as quickly as possible about matrices and determinants and how to use them. So basically, some more stuff in linear algebra and how to do it. Which math chapters are you guys through at this point? Have you guys done?
I think we did math chapter. We did the one with
the matrix eigenvalue. That's F. So E is determinants.
I think E is spherical coordinates and spherical.
Have you done anything with determinants yet? Okay. I'm going to race through this regardless. So if there's a math concept that comes up in here that you aren't familiar with, go check the book. I'm a little bit potentially ahead of what Joe is doing in class, but I really am not going too in depth into any of this other than to just show that they exist. And when you run across it in the textbook or in life, you're like, I need to take a determinant or I need to multiply two matrices together. You can just punch it into programming language, Julia, MATLAB, whatever it is, and it will do it for you.
When I try to open up the matrices and determinants, it says 6 seconds
Hmm?
It won't show me. And then I click in and now it's just muted.
Oh, you haven't gotten the latest code.
I've been trying to update it this whole time and I don't know how to pull it. I forgot.
So,
Alright, thank you.
so I'll show everybody. Most of you probably aren't using Git to get the latest versions of this, but if you're wanting to pull the latest code, you can type git and pull, and that will pull the latest code that I have up on my repository. Most of you, I think, if you're using VS Code, are probably just going to the repository site and pressing download, but either way works. Just kind of do it before or after if you see the video, the code will be updated. So anyway, matrices. So a matrix is, so we've dealt with vectors / arrays, which are essentially just a special case of a matrix or a vector, a matrix or an array, in that it's a one-dimensional array. So you have one row by some number of columns, or n rows by one column, either a row vector or a column vector. A matrix can actually be n-dimensional. We're just going to stick with 2D arrays or 2D matrices for right now. So you've got n by n. They don't have to be square matrices, but everything you deal with in quantum mechanics is going to be a square matrix, because the properties of Hermitian, all this other stuff actually require even more stringent. They have to be symmetrical matrices. So this wouldn't be a good quantum mechanics matrix, because these have to, I think, at least be complex conjugates of each other. Don't quote me on that, and I should know that. It's kind of embarrassing, but I know they have to be at the very least symmetric. So there are two ways to define a matrix in Julia. So A is just going to be our dummy variable for matrix right now. You can use this syntax where you're using multiple lines. You've pressed enter, and so you've got your rows here, and then you write it in a column. But if you don't separate them with commas, they're only separated by spaces. And then you use semicolons if you want to do a row, do them all in one line.
Can I index the first column, third row?
Get one of them, pop the value out or put the value in. Yeah, I'll show you how to do that here in a second. So there are several. These are just various functions that you can do. So a trace of an array or of a matrix is going through the ones where I equals j, so down the diagonal, and then I believe it sums them. Let's go ahead and run this. I believe a trace is a sum. Run. Julia will load up all of its things that it cares about. That's why you should press play before the video. Yeah, so -3. So if we add in our matrix 0 plus -3 plus, 0 plus -4 plus -2 is 6. I'm bad at math. -3, 1 plus -4 plus 0, 0. So 1, 1, 2, 2, 3, 3 is equal to -3. The determinant, you can look up the formula. It gets more and more complicated as things go on, but it's this plus this, that plus that. It's a bunch of slanty sums, but you don't ever have to think about it again, because you just make your matrix, pass it to the determinant function, and it gives you the value. You can also transpose. So a transpose is you flip it. So if something was in the index 1, 2, it would then go into 2, 1. So you flip the matrix over the diagonal. So the diagonal elements stay the same.
Yeah, anything that's I equals j.
Yeah.
And what's the inverse?
The inverse is the same thing as if you were to do, like if you have a formula x, y equals z, and then you made that equal to x equals to z divided by y. The inverse is the same thing as division, so you've put it in the denominator. You'll see in a second we're going to solve a system of linear equations with a matrix. And what you do is you do a, so here's another way to think about it. So you have an array times, I guess I'll just do this, inverse A. What do we think that's going to be equal to?
The identity matrix.
Yeah.
Believe it or not, I actually said the same on all of this stuff. So I'm actually
Oh, I forgot to, it'd be good if I displayed it.
why does really it take so long to do these functions? It's not.
So Julia is what's called a
So when it like 5 to the negative 15 is very close to 0.
yeah. Why? Oh, it's because I have a println in here. For some reason, Jupyter or the Jupyter notebooks, when you put a println, it goes above the. So notice these numbers are all very, very small. So that really is the identity. This number should round to 0. I will take your question of why Julia is slow offline because it's a complicated and unnecessary thing for you to know in the class. If you mind waiting on that. The in general thought, though, there before I move on, is that it is a fast language. Just some of the upfront stuff can be slower than, like if you had a compile, like it's doing all the compilation type things every time because it doesn't compile the code, is the short answer to that. And it's doing a lot of fancy stuff. But anyway, here is a couple of other things. So this is what you're asking about indexing. So you have row, column. I defined these. So we have a matrix, and then we're getting the value at that specific spot. Excuse me. So 1, 3 gave us the first row, third column, which was 3. The third column, first row is 7. Printed that out. So that's how you. So you can imagine if you were trying to loop over all of them, you would have a for loop of I and then j, and then you would, for all the i's, you get, if there's 3 by 3, or I is 1, then j is 1, j is 2, j is 3. Then I increments to 2, 1, 2, 3, 3, 1, 2, 3, and then you would have indexed through all of them with 2 loops. And then I just printed this out so it's easy to see them next to each other. So we've got the indices as how you would index them to get the values above. Yeah, you can put anything you want in a matrix. So if I want to, you can define something that's not. So I could put string matrix equals matrix string undefined 3 by 3. So this is going to create an empty array. So I could put this as 0, initialize it that way. So now we're going to get a 3 by, oh, that's not going to work because that's not a string. How about the string 0? It doesn't like that. There's something wrong with this syntax, but it's something similar to this. I think I potentially use it below. We'll see it, but essentially, you make a matrix. I wonder if array works. I should know this. I was literally doing this today. Let's start with undefined. because it liked that. So we did undefined, and then we can do string matrix sub 1 1 equals hello display string matrix, and then it put that in there. So you define what type you're going to put in there. You undefined, basically we're just making an empty thing, and then this is a tuple, so it's a construct of a tuple. Although it sounds like the word two, this is also a tuple. You can have, it's just many things collected in a, it's essentially a cheaper poor man's array would be a way of thinking about it. We use a tuple to describe how big the matrix is going to be. So the dimensions, you know, rows and columns. Moving on, you can also, I didn't put a note here, you can get the rows and columns of a matrix as so, using the key in place of a index. So when you place the colon, it just says give me the whole thing. So give me all of the things that are in column 1. Give me all of the rows, or sorry, all the columns for row 2. So when we run this, these will come out as one dimensional. So you'll see that it's printing them out this way. You're pulling a vector, so you have to conceptually know that what you pulled was either a row or a column, because it's not gonna, at the end of the day, it's pulling it out as a vector, so it's an array. So it's, you can think about it as being a row or column vector in your head, but it's just a list of things. But so we have
an easy way to flip a vector between a row and a column vector.
I mean, that's more conceptual.
Like it's like
oh,
in MATLAB you just
yes. I think Julia will probably just figure it out. So if
okay.
I'm gonna test that.
Because I mean that's kind of nifty.
I'm gonna try to add these and see if it, because there's there's multiplication rules, right, where you can't. So I know you can do B plus C. That will work.
Yeah,
It didn't. Yeah, that was right. And printed it out.
did it?
Yeah, that's it. It didn't do this stuff above. It doesn't. Jupyter by default prints the last thing if you define it and don't give it a. If you didn't print it in a different way. If I did B times A. Yeah, so the dimensions didn't work, so you would do then transpose B times A. That was the answer to your question, was transpose.
Okay.
I just couldn't remember what the syntax was.
Okay.
Good question, thank you for asking it. I'm going to leave that there. I think I may have, yeah, I just skipped over it. We transposed something up here. Oh, we talked about it in terms of matrix, and then you can transpose a row and column vector because it changes all of the indices.
Okay.
It turns it from a row to a column vector. Yeah. Cool.
Oh, because it's like
1
1 1 1 2 and 1 3, and then it goes 1 1 2
1. Yep. Okay, so now we've got two matrices, so there are operations that we can do with those. So in class, have you guys talked about matrix multiplication yet? Probably not. If you haven't done determinants, you probably haven't done matrix multiplication yet.
All we did was the cross product of two vectors, not matrices yet.
Yeah, so a cross product is very similar to, or might actually be definitionally the same as matrix multiplication, but you can essentially think about it in the same way that you think of multiplication of two scalar numbers. It just has more rules to it. So if you did a 1D matrix multiply by a 1 by 1 matrix by a 1 by 1 matrix, you're going to get the same thing as a scalar multiplication. So if you had 1 times 2, you would get 2. It would be in the square brackets. So there's a more deep mathematical formula, more complicated, I guess, than deep, that does it. But the good thing about code is we don't really need to worry about what the formula is. It's just doing it for us. We may need to know, and we will. So what we're doing here in the exercise here in a second is using matrix multiplication. So a times the identity, this is the same thing as doing like a times 1, so you'll just get the same thing back. So Julia reserves the keyword capital I for the identity. So this is actually a special thing. So if you were to just look at this thing, it's its own kind of matrix object that it just knows, because it is what it is, to just basically not do anything to the thing it's multiplied to. So it's not actually storing a bunch of zeros and ones on the computer. It's just a computational, like, it's a class or an object or whatever that we don't need to get into inheritance quite yet. We'll get into it here later in the topic tonight. But it's its own special fancy thing that makes it do things faster because it doesn't need to do anything. So it just doesn't do anything. So then we have the a times b, as we talked about, multiplication. But then you also have, so last time I introduced like element-wise, that ham-hard product where you just take, the first item and multiply it or add it to the product with this dot and then the operator. So you have the same thing for matrices, so you could still do that same kind of product where you did 1, 1 times 1. So 1, 1 of A times 1, 1 of B, and then put that into the result. And then 1, 2, 1, 2, so forth. So I printed those out. And then this gets back to that, what we were talking about of the inverse, farther down than I was ready for. Inverse, so you can do A. So this is not a /, this is a \. So this is a shorthand for doing inverse. Oh, I wrote it in the comments. So this is equivalent to doing inverse times B. So this is just it's a shorthand that's used everywhere in these kind of linear algebra circles. So they just implemented it like this. This is equivalent to so we had A times X equals, let's even do a better one, H times psi equals SCE. Jeez. Yeah, so how this ends up, you can then put this over here as h to the -1, essentially, which is that same thing as that inverse. Again, we're using some maybe less than stellar way of writing this, but then you get h equals to that. So something we might end up being familiar with. A more simple, as opposed to that was an eigenvalue equation. If we're just doing a system of linear equations, we're about to get to this. In the same ways, you can write x times b equals, x times a times x equals b. You can then do x equals a to the -1 times b, so that's that inverse, which is equivalent in Julia to this syntax that we just did. So you can then get the values of x. So that x is a vector. This is a matrix. This is I believe a matrix. Maybe it's a vector. I don't remember.
It's a vector.
Yeah, it's 2 vectors and a matrix. Yeah.
Finally, that makes sense. The a backslash. I've been using it, and I know that it will solve systems.
It's a shorthand for a left inverse, because in linear algebra the order of operations matters. So that was what I wasn't writing. So in all of this we would have step that makes this actually make sense is that you also on this side raise this to the -1, which then these two cancel because the inverse of something, operating on the same thing will give you just the identity. So that goes away, and then by left multiplying, so it has to be on the left side, so you've left multiplied by the inverse is what that \a is. It's the same thing as writing inverse a. So, did that make sense, or was that more confusing?
No, that was actually because that's what we do is we take the
you have to take
complex conjugate of it and then apply it, and then boom.
Yeah, the inverse, not the complex conjugate.
Well, I mean, when we're integrating over in chapters 1, 2, 3, 4.
Different thing.
It looks very similar.
It's the same thing. It's the same thing as in arithmetic, where you multiply by 1 over the thing is a better. But anyway, moving forward, we're going to talk about this again. So you guys have not gotten to the eigenvalue and eigenvector equation slash. Eventually, so when we're solving the Schrodinger equation, it's going to turn into one of these eigenvalue, eigenvector equations. I think he might have maybe briefly talked about it in the beginning of the class, but essentially you're going to multiply a matrix times a vector to get a vector times the energies. So the eigenvalues are the energies that are the solution to the Schrodinger equation back times that same vector. There's one vector that represents the wave function, and then you have a vector that's the energies, and then a matrix that represents the Hamiltonian operation. We won't get into the gist of it, but at the end of the day, you can. So, and then that when we do it on a computer slash actually solve an eigenvalue equation, that all gets turned into one matrix, and then we solve the eigen. So you just call the eigen function, the function called eigen that gives you the eigenfunction and the eigenvectors and eigenvalues of the matrix. Again, you don't need to worry about the specifics of this. Just when you get to there later or want to use it, just know that you can come back, and it's very simple. Just set up the matrix, pass it into this function called eigen, and you will get what you need. So now for something that's actually applied, you've probably at some point in some sort of algebra or calculus class been forced to do some sort of system of equations. And here I am to tell you that all that hard work that you did, you never have to do again, because you just turned it into a matrix equation, let the computer solve it for you, and Bob's your uncle. So we have this system of linear equations. So we have x1, x2, x3. So we have 3 equations, 3 unknowns. We make an A matrix, so our coefficient matrix. So 1, 2, 3, 2, 3, 2 matches with those. We have B, so a matrix representing the right-hand side of the equality, and then we have our x vector that's our unknowns. You have A, B, so we started with AX equals B. We can then take A inverse multiplied on the left times B, and then that will give us X. We will get the solutions that come out here, and we can then test it using one of the original equations, multiply it by 1, 1, 1, 2, and 1, 3 by x1, x2, x3, and see, make sure we get 2 back, and wouldn't you know it, we got the value. So our solution to our linear system of linear equations was correct. This is super powerful because there's so many different things. You're mentioning chemical engineering, so when you talk about reaction engineering problems, you end up with a system of differential equations, which you can then convert into a system of linear equations, which you can then convert into a matrix equation, solve on the computer, work your way backwards, and then you've solved your system of differential equations, which is super nice.
Isn't that how you can do like stimulus and response and stuff as well?
This is this is chemical. The solutions to chemical engineering problems in a nutshell. It goes to everything and everywhere. Basically, science and computers is all about turning hard paper and pencil math problems into matrix equations, and then having computers solve the matrix equation. That's one of the main ways of solving things. So, a little history lesson. This is actually what the Anna A. Tanasoff Berry computer built on the Iowa State campus was created for in the 1940s. Was to solve systems of linear equations. Yes, 1940s. You read that number correctly. That was a long, long time ago. It's hard to. There was a lot of things going on in the 40s with computing, early things, but it's potentially claimed that this was the first digital computer to make actual solutions to physical problems. So, pretty neat stuff happened right here on this campus. So
The computer was the size of a building.
No, this one wasn't huge. There were computers in that era or right after it that were more powerful. I might be thinking about like ENIAC or things like that. Those were like the room-sized computers.
Stop also right there.
Yeah. I mean, it's big. I'm not saying that it might be as big as this room, but when I think of computers as big as a room, I'm thinking like there's like a whole warehouse of things to be able to do.
Well, I remember like the first computer that was literally the size of a building. They were loading like a 1 byte memory thing off of a truck.
Yeah.
And now this has got like
Yeah, there's
gigs.
yeah. You're on the right order of magnitude there were a lot of things. So there was like the I forget what thing that Alan Turing worked on to solve the Enigma machine, which was an analog computer, the first digital computer I don't remember the name of, but this computer that we're talking about is among the first like 10.
Oh, nice.
Yeah, it's
Digital.
Digital computer.
When we made rocks think with electricity.
Yeah. Well, analog computers also were run using electricity. But anyway, that's a digression that we don't have time for.
So are we gonna do like the integrals as well?
I am saving that for. I have. Oh, this. Where did I put that? Did I?
Yeah, I don't know what you did with it.
I don't know where.
It was on this, and then it was gone.
Yeah.
Because once you hold it, it was just gone.
I have. It might have gotten lost in my. I think it got lost as I was changing this file. I will resurrect it. If you're interested, I'll make a special video for that one, because I wasn't planning on going over it today.
Oh, no. You said that you said we were going to go over it today. No, we're not.
No, we're not. Sorry.
So don't make a video, because if we're going to cover, we're going to cover.
No, I don't think it's not something I'm going to cover specifically anymore. Some other stuff got pushed ahead of it. No, but I will, because there is an optional exercise, and I want to walk people.
For like an extra credit?
Just if you're interested in doing it, type of thing, to get more practice with loops, essentially. Yeah, I don't know where the. Anyway.
Familiar to calculus.
Yes. I will resurrect that bit of Jupyter file regardless, so it's there. The main topic that I really wanted to talk about, is less practical and more, wonder if it accidentally got at the bottom of this. Nope. Is to talk a little bit more software engineering topics. So this is kind of you can sit back, relax, you're not going to have to do any of this stuff. This is stuff that one needs to know, and I'm of the opinion it should be given very early. If you were taking a computer science course, you might get some of this object-oriented stuff, but maybe less of the design pattern stuff until you were like a junior in a computer science program. But I think it is super important to understand how to write good code very early on, and kind of some of the central questions of how you should think about writing code and what you're doing, and what you should be asking yourself as you're writing the code. So I'm going to spend the next half hour or so, it might bleed over. I may go a little bit long in the lecture this time, but the homeworks will be correspondingly shorter this week. We're literally just going to be punching matrices and vectors into those into those functions, and printing them out. So nothing too complicated. So you can have a little bit of a rest this week. As last week's problems were certainly pretty challenging for it being the second module, really. Anyway, so design patterns. There's a central question you should ask when you start writing any bit of code, especially early on, is which type of thing are you doing? Are you doing what I will call scripting, which is really just kind of a single use, not necessarily throwaway, but something that's not overly complicated, it's just trying to perform some single task. Maybe you're trying to, instead of having to do a bunch of stuff by hand, script it so the computer will do the repetitive tasks for you, but you're not building anything of high complexity. That's on one end of the spectrum. So these two things are two sides of the same coin, or a spectrum, because they overlap, and the concepts don't necessarily have to be exclusive to one or the other. But when you're on the other end of the extreme, where you're building out something like a larger code base that does many things that are going to maybe be used by other scripts or by other people, or basically just anything that's not just kind of single use, it's something that's like, so the thing that I'm working on is called Julia Chem, or the other thing that I work on that Dr. Gordon's group has been working on, which is called Games. It's the 40-year-old code base that has something like 3 million lines of code. If you're in anywhere even between, once you start getting past like 3 or 4 files, this stuff pays dividends to be doing things right. It saves you lots of headaches. So if you're on that end of the spectrum, you should definitely be thinking through the concepts of designing your code base well. So one of the most widely used, most popular paradigms is what's known as object-oriented programming. So I linked off to the Wikipedia page here if you want to read more about it, more of the theory and some of the other stuff. But at the end of the day, what OOP boils down to, especially when you're just getting started with it, is that an object is something that encapsulates some amount of data and some operations that you can do on that data set. So the word that we use to describe that is a class. So you can think about it in terms of types of things. So there are classes of animals, say. So vertebrates, where life has classes. Animal kingdom has, lions are in the same class as domesticated cats, dogs, and wolves types of class. So they all have individual attributes and might be different than each other. So you start taking the world and boiling it down into classes of things that are the same and can have the same operations on them. So you could think about maybe people, classes of people, like a teacher and a student have similar properties, but there are some things that a teacher can do that a student can't do, or there's a lot of different. At the end of the day, what you're doing in programming is you're trying to model the real world, the data that you care about that comes from the real world, the attributes, and do things on that data to get some result. So the object-oriented, the class structure is how to organize that functionality and data into discrete packets so that there is some set of organization. Quick caveat, Julia is not explicitly an object-oriented language. There are languages like C++, C#, Python, I believe. A lot of languages in the modern day have built-in object-oriented functionality, and they kind of are forcing you to be object-oriented. Julia kind of comes from a different paradigm and doesn't force you to use object-oriented, but an object-oriented language is not necessary for doing object-oriented programming, or at least using the concepts to inspire the way you write your code. So just strictly going off of this object-oriented programming paradigm, that there are conceptually data and functions on that data that go together. That's all we're really going to be worrying about, and all you really need for thinking through this. So I have built a couple of simulations that show some good organizations versus bad organization. But before we get there, we'll think through the simulation. So I have simulated, or we as a group want to simulate very basically just some bicycles that are out on a two-dimensional plane moving around. They can either go left, right, up or down, positive, either forward or backward in either direction. But if we were thinking about this in terms of like a real simulation, there might be a lot of things you would want to know. So attributes about, I switched from car to bicycle in the middle of this, so there was a...
Yeah, I was like, we're talking about bikes, and then bikes got a VIN number, and I was like, okay.
A bike does have a VIN number.
Does it?
Yeah, I actually just bought, I have my new road bike just got shipped to me this week.
How much does a road bike cost?
I will tell you that offline.
I can imagine. I'm considering getting a bike for after I get back from my co-op.
I love bikes. I could talk bikes all day. You can tell because the first thing that I thought about in simulation was a bike. Actually, it was a car, and then I was like, no, let's do bikes. Anyway, so a bike has a color, gears, wheel diameter. None of these things are going to change. So these are kind of immutable properties about the thing. Immutable meaning not changing. Then there's other properties that might change. The speed it's moving on the road, the position, what gear the bike is currently in. Believe me, we're not making a simulation that's this complicated, but there are, simulators out there, flight simulators and like e-biking racing platforms and all that would be doing this kind of stuff. So what functions could we perform on a bicycle? Maybe speed it up, push on the pedals, slow it down, hit the brakes, steer right or left, change gear, update position. So these are the kinds of functions that go with this data. So the bike has things, attributes about it, and we can change those mutable attributes by applying some functions to it. So then we think about, in our code and our model, what is the kind of thing that would change the gear or would speed it up or slow it down? So that's a rider, that's a person. So the bike doesn't pedal itself, so we would have some grouping of functionality that applies to a bike that we could lump under the category of rider. There's other things like the world or the simulation class, like the wind might be blowing, and that could impact what's going on the bike. Or there's other riders, so all that kind of stuff can get in. And but the world simulation class isn't going to pedal the gears. It might have some other function that it does on a class. So that's just a way of starting to suss out what different things and where different code should live is based on what kind of class of thing it relates to. So here's a question for you. What class should keep track of positions and velocities of the bikes over time? Yeah, the world. So the simulation would be something that would keep track of that. How would any of this thing that I just talked about, modeling, how would that change if we were talking about a sailboat instead of a bike?
That a serious question?
That is a serious question.
We could spend one.
Well, yeah, just give me an example.
So I mean, like, obviously you'd have to have like our ocean,
Mm-hmm.
and like drag on the boat from the ocean, so the wind.
Yeah.
Is there a motor on the boat? The direction of the wind.
Yeah, so let's think no motor. So what moves the sailboat? Yeah, so the environment moves. So there's
also the angle of the sail.
Yeah, exactly. Mm-hmm.
Is anchor down?
Is the anchor? Yeah. do we have the kickstand on the bike down? Which no, because you shouldn't have a kickstand on your bike.
Kickstand on your bike?
No, not on a road bike.
Oh, it's a road bike.
Yeah, we're racing around. Well, I guess you could have a regular bike that has a kickstand, and it would have a larger coefficient of drag because it's got a heavier weight. But nobody's racing around with a kickstand. So I made two simulations. One that does all of the code, all of the simulation in one function, and then the other that is using some of these object-oriented design patterns. And hint, hint, the one that's on all in one function is not how you should write code. So the first thing that I always kind of think about when I'm thinking about writing code, well, we're skipping ahead. I want to show this to you and then introduce some of the concepts, but I think I've mentioned this before, but there's a concept called the single responsibility principle that at the end of the day, I think almost all of the design patterns boil down to that one thing. There are other more esoteric ones that are important, but the ones that really, really matter and should be understood by everyone that writes code is that a thing, a function, a class, and whatever should have one purpose and one purpose only. So we can already see, I mean, if you don't even look at what's going on in the code, the fact that this function is already the size of our screen and we have to scroll means that it's probably already doing more than one thing. There are exceptions to this, and there are times where it does make sense to have a really long function because there's no good way to divide it up for performance or whatever. But when you're really first starting, and almost I would venture to say 95% of the time there are ways to find places where you could divide something up into another function. So first test, if you have to scroll to see your function or your class or your function is probably too big. But anyway, so let's simulate some bike movements. So we've got a couple of variables that we're initializing here, and we're gonna initialize a bunch of bike positions, X and Y. So we've got two arrays that keep track of a bunch of places where the bikes are, looping over there randomly. So I'm using this random module that Julia provides. It just generates random numbers. So this generates a number between 1 and 100. Don't worry too much about that. Anywhere where you see something like rand, or it's just generating random numbers, and I will talk about those in a minute. And you'll see another thing of like, because there's no comments and there's no function names, the only thing you have to go on is really the variable names to tell you what's going on here. So that's another thing about having lots of a function that's really long. You can lose track of what's going on, because if you were able to break it up into other functions, you could name those functions and it would be more descriptive of what's going on in the code. But anyway, I digress. So we've initialized where the bikes are in our space between 1 and 100. Initializing a bunch of data for all the simulation steps. So this is where we're going to keep track of where the bikes are in time. So this is where they are currently. This is where they are in time. So we'll keep track of, at the end of each run through the simulation, we'll keep track of everything, and then we can print it out over time. So for t in 1 in simulation, so t being our number of seconds, or tens of seconds, or whatever your definition of what a division in time is. And then for each bike, for bi bike index. So as I've said before, index variables are bad, or like undescriptive names are bad. So that's already a thing that's unhelpful about this, because we're using a shorthand, but easy to figure out if you put a comment or something. But just pointing that out as another thing that's not really great about this. So we're initializing our new X and Y with the current X and Y, and then bit random gives a yes or no, so or a random number, or a random Boolean. So randomly we'll change the X or Y each second, so the bike rider might want to go a different direction in X and Y. So they're just making a decision. So already something, even by talking about it, I'm saying this is a bike rider, but in our simulation code, there's no concept of bike rider. It's just, for some reason, we're doing an if here, so that's not very descriptive. So if we're going to change X, get a random new position of either going left or right in X, checking if you're inside the max dimensions, so staying, greater than -1, meaning 0, or less than 100 plus 1, so between 0 and 100. So staying in our 2D space, can't go off the cliff kind of thing. Then doing the same thing for Y. So right here, what jumps out at you about that? Those look very, very similar in the structure.
Yeah.
Those seem like a pretty good candidate for something that might be a function that you didn't have to write twice.
Probably.
So when I was writing this, I basically copied and pasted this and then changed everywhere that was X to Y. If you ever catch yourself doing that, you're probably doing something wrong. It's not a hard and fast rule, but when you're copying and pasting, unless you're copying and pasting to move it out to another function, you're probably doing something wrong. Not always. I use the copy and paste function a lot, but
Sometimes it's fine.
this is bad. This whole thing is bad, but that's particularly bad. So then we're going to check if we're making a collision with anybody, so checking the position of the other riders, and if there is a collision, we will leave the new time position will be the same position. Otherwise, we will move to the new position, and that will be the step at that time. And then at the end, we print out all the stuff. So we can already see right here, there's two definitely separation of concerns. That's a term for keeping things in their right objects, is something called separation of concerns. It's a keep the things that are related to each other near each other. In the same way I'm talking about single responsibility principle, is like the things that don't need to know about each other should know about each other. So this class, this function, this Julia file knows both about how to simulate things and then how to print the simulation stuff. So that's already your first thing. It's like, oh, those definitely should be split out into their own modules or whatever. So now we can talk about the concepts so that we would have violated here. Interesting. I need to switch branches of my code because I definitely lost some things from what I was talking about before. Technical difficulties.
Like the
I love.
object-oriented programming, or?
Yeah, I mean, I can talk about this without. I can just go to the Wikipedia page. I had some notes about it. Boo. Anyway, that's really annoying. I will make sure that my notes are up there, but so I'll just go off to this link, which is Wikipedia, and I really actually want.
Good, you use Microsoft Edge.
Yeah. So there's this acronym called the SOLID principles. So they're a mnemonic device for remembering the 5 kind of most important principles in object-oriented programming. So I talked about that first one, the single responsibility principle. There should never be more than one reason for a class to change. So in other words, every class should have only one responsibility, and the only reason you would want to change that class is because your requirements have changed, or you had a bug, or like the thing that it was doing, it needs to change, as opposed to it does 2 things, so we're going to change one of the 2 things. So if you had 2 things, it should have been split into 2 separate classes or functions or whatever. Then the O and the L are not really relevant to you guys at the moment, but so then there's the interface segregation principle. So in a class, you can have many functions that can. An interface is essentially a contract between the caller code and the code being called. So it's better to have a bunch of interfaces that do one thing as opposed to an interface that does a bunch of things. So it's kind of a rephrasing of the single responsibility, in my opinion. In object-oriented programming languages, there is an actual construct called an interface, or sometimes it's called an abstract class, depending on the language, that says these are the things that my class can do. It's better to separate those things out into smaller interfaces. In Julia, that's less of a big deal because you're already not really using interfaces as a specific construct, but we'll see an example of this in my code where I can kind of shoehorn into this idea, but just nailing it home that if you're using an interface, so another way to think about it is if you wrote some code that was a module and it could be used by other modules. It's better to not just say, hey, I am this interface and here are all the things that my module that I built can do. You build sub interfaces. So like let's think about the random interface, or here, how about this? If you built a math library, Julia has mathematical stuff, but they have a specific library for linear algebra and statistics and all this. So it's not just one giant math library that you can do all those things. There's a linear algebra interface and there's a statistics interface. So that would be kind of how to think about that. And then there's the dependency inversion principle. So depend on abstractions, not concretions. So in the same, so that interface we talked about, it's the contract. The only thing that the caller code should know about the called code is that interface. Pass me X, Y, and Z parameters, and I will give you back some new thing, or I will modify the X, Y, and Z parameters. It should know nothing about how it does it, how it implements it, how it stores data. Anything behind the interface should be totally abstracted away from the thing that's calling it. So obviously you can't do that as a programmer in your head. If like you know what you're calling and but you have to think about it almost from the perspective of somebody who's calling your code outside of it, like that doesn't see the source code. It should just be totally separate. So there shouldn't be like one thing that often happens is like you pass it, like you have a function and there's some if condition in there, and to like make it work, sometimes you just pass in another Boolean to try to go down one of the two paths. It's better to try to split that into two functions that know how the inside of the interface should know which part of the code to call, and you can rename the function or something like that. So that's one example of knowing, like that's a code smell if you just keep adding more Boolean variables onto your function to like try to go to different parts of the function that you're calling. That's kind of a code smell. Is a we use that wording to mean like something is probably wrong with the code. It's not necessarily wrong, but an indicator. So with all of that in mind, I wrote a somewhat object-oriented version of this. So you can already see there's some organization. So we have our script that's running this. So I run the simulation. We then have a simulation file so the data that I was talking about, we use a construct called a struct. So there's no classes in Julia. So in other languages, you would have a simulation class. The class would have data and functions in it. In Julia, you define structs to keep your related data together, and then you have related functions that use those structs to actually perform the operations. So I have a file called simulation operations. This is a code smell. So the fact that I just called this operations, you could put anything related to simulation operation, an operation in there. I call those dumping grounds. So if you don't name your file something that means something specific, the next person that comes along in the code can just put whatever function they want in there. Like, yeah, it was, it's a simulation operation. So I wasn't thinking about that when I wrote that. So I call that, I'd be misusing that term, but I like to be defensive in that way. Is make sure to use specific names for things so things like that don't happen. So like for instance, so I have the simulation runner. So this is what we call the operation run simulation. You pass in a number of bytes and a number of seconds, and it will run the simulation. So we have this in the same file as print results. So I could make another file. I'm not going to do all of this, but you could make another file that's like simulation result printer, and you could move that file out into that. So that would be an even better improvement on what I already did here. So we're running simulation, and you'll notice that the functions that this function is using are above that function. So just another organizational thing you need to do. So running a simulation, we initialize our some simulation object. So this is just making that struct. But if you didn't care about how it gets initialized, you could just move forward. So there was all that code that you would have had to have read that was making all those arrays and all that other stuff. If you didn't care about that, you're just trying to understand, what the results were, you wouldn't need to think about that. So that's a benefit of making functions that have good names. So we can run a step. So that runs a step. So it goes through all the bikes. It moves the bike. Where do you think my move bike function is?
Under simulation.
Rider. Remember how we're talking about a rider is the conceptual thing that moves the bike. So we have our move bike operation. So all that random number generation of whether or not I should move. So I brought that one function that I copied and pasted, and I made it generic. So it gets a current value and then potentially, based on the random number, gives a new value, or it doesn't, it returns just the current. So and here's the check if you're gonna make a collision. So get random position, check if there's a collision. If there isn't a collision, move to the spot or stay in the same place depending on the result. Simulation operations. So we're in run simulation step. Increase the simulation time, and then that's the end.
How long did it take you to code this?
This was the first one was probably an hour and a half. The second one I was copying and pasting. It was probably another hour and a half. It shouldn't have taken me as long as it did, but that's another thing. So when writing code, however long you think it's going to take you, double that at least, and you'll probably be in the right order of magnitude. It's very people spend their lives trying to understand how long it's going to take developers to finish writing code that people have asked them to write. There's whole professions around it, and it's voodoo sorcery, and nobody can ever really come up with good answers. It's very, very hard to predict all that kind of stuff. It wouldn't be fair if I didn't run the simulation and show you that it actually works.
Oh, it works. I ran it twice.
Well, there you go. You ran it. For the folks watching at home, I really wanted to make this a graphical thing. And we're going to talk about plotting in another module where you can plot things, and we could have done this in a plotting library.
Can't you just plot it? Like, how long would it take you to plot all this data? You already have it all stored.
Yeah, it wouldn't take that long. So then that's the thing. So
That would be under the rider, then you would plot the.
no, that would just be result plotter. That would be its own kind of module, is how I would put it. But yeah, so I simulated a bunch of positions and printed it out. There it is. So that is all I really wanted to talk about today. Let me go back to. So I will upload a updated version of this sometime tomorrow or the next day with the exercises. They should not be very hard. They really should be just like, I think I'm going to take some problems from the textbook, change the numbers, and then have you guys punch them into the functions. So look out for that, and I will send it in an email. Any questions from you before we log off? All right. Thanks, guys.